Stoichiometry, a very, very important topic. And it combines two things that we've just learned about, balancing equations with conversions. And when I say conversions, it's specifically moles, grams, particles, and we're going to put volume into there, volume of a gas. We're going to use this throughout. It's probably the most important background information that we need to be very, very comfortable with. Let's take a look at a simple example here. We could say, one atom of carbon will react with one oxygen molecule to produce one carbon dioxide molecule. So that's a very simple example, very, very small. We're not going to do, we could not do this because of how small the atoms are. But instead, what we're going to look at, we can kind of scale that up to a mole. We could look at a dozen if we wanted. Again, that's way too small. We're going to look at 1 mole. So 1 mole of carbon, that is 6.02 times 10 to the 23 carbon atoms, will react with 1 mole of oxygen, again 6.022 times 10 to the 23rd molecules of oxygen, to produce 1 mole or 6.02 times 10 to the 23rd carbon dioxide molecules. We can also look at mass, since that is a little bit easier for us to measure out. That is very, very useful, obviously, in the chemistry lab. 1 mole of carbon weighs 12 grams. We get that from the periodic table. 1 mole of oxygen weighs 32 grams. 1 mole of carbon dioxide weighs 44 grams. If we notice, mass-wise, whatever's on the left-hand side has to equal the mass on the right-hand side. Again, we know matter is neither created nor destroyed, just changes form. Let's look at now a little more, we'll actually have to do some math here. A mole-mole conversion. These are the easiest type of conversions for us. Consider the reaction between aluminum and oxygen to produce aluminum oxide. Write a balanced reaction. All right, so first up, we have to think about our reactants. Our reactants are aluminum, Al, oxygen, O2, and we're going to get aluminum oxide. I know some of you are going to just write AlO2, just put them together because that's easy. That is wrong. Instead, what we're going to do is we're going to think back to how do we write a balanced formula. Aluminum, I know, is going to form a 3+ charge. Oxygen is going to form a -2 charge. So now when I do the switcheroo, I get Al2O3. Now that I have written balanced formulas, now I can look at balancing the overall equation. All right, let's see. I have 3 oxygens on one side, 2 on the other. Hopefully you're all yelling at your computer saying, make them 6. So whenever you have 2 on one side, 3 on the other, we're going to have to make them a total of 6. So we're going to put 3 O2s over there, 2 Al2O3s on that side. That changes it so that now we have 4 aluminums. So here's our balanced equation. Part 2, if we react 4.6 moles of aluminum with excess oxygen, how much aluminum oxide can we make? Excess oxygen means we have like a cajillion billion moles of oxygen. It will not limit us. Instead, what's going to limit us is the aluminum, so that's what we have to worry about. So we're going to start with 4.60 moles of aluminum. Now let's just think about units here. We have moles of aluminum. We want to get or finish up with moles of aluminum oxide, Al2O3. I know I need a conversion factor because we just said stoichiometry deals with conversions. All right, let's just think about our units for a second. I have moles of aluminum on the top. Or I'm sorry, I'm starting with moles of aluminum, so I need moles of aluminum on the bottom so that they cancel out. I want to get moles of aluminum oxide, so those need to go on top. Very simple. Easy so far. All right. Now, what numbers do I put in here? Well, that's where the balanced equation comes in. Whatever my coefficients are, that's what goes in with my into my conversion factor. So moles of aluminum oxide, I put a 2. Moles of Al, I put a 4. So my conversion factor here comes from my balanced equation. All right, because here now my moles of aluminum would cancel out, and I'd be left with moles of aluminum oxide, which I'm looking for. Hopefully none of you have grabbed your calculator. 4.6 times 2 over 4, that's half of 4.6. Hopefully we recognize that. 2.3 or 2.30 moles of aluminum oxide. So what we're saying here, in our conversion factor, we'll just look at that for a second, we're saying that for every 2 moles of aluminum oxide formed, we need 4 moles of aluminum to start with. So here we're starting with 4.6 moles of aluminum times the 2 over 4, units canceling out. Again, we get our conversion factor from the balanced equation, and we'll be left with 2.3 moles of aluminum oxide. Simple example. Now what we're going to do is we're going to take another step further, and we're going to look at grams, or we're going to look at mass involved in our calculation.